Welcome to lecture number 8 of the course Trend in Modern Cryptography. I am Roberto Civino from the University of L'Aquila, and this lecture is entitled Learning with Errors, SIS and LWE. So we know that when it comes to security against quantum computers, public key crypto systems, which are based on factoring or on the discrete logarithm problem, are not secure. So for this reason, we are interested on new problems, which are also difficult for quantum computers to base new crypto systems on. In this presentation, we will discuss mainly LWE, which is today one of the most popular underlying problem, if not the most popular underlying problem, which post-quantum crypto is based on. LWE is a lattice problem, as we will see. So to introduce the notation, I will quickly recall that a lattice is basically a grid of points in R to the n, satisfying properties that you are already aware of. With the word shortest vector, we mean the shortest vector, which is non-zero with respect to the norm in L2. And we also know that every lattice has a dual lattice, which is defined in this way here. We will see later why this dual lattice matters in this context. There are many difficult problems which are related to lattices and in particular to their shortest vectors. Here we need this specific problem, a decisional of the SVP in its approximate flavor, which is called GapSVP. And this is the problem where we are given a lattice by its basis and a function gamma of n, and we need to establish if the given lattice has a shortest vector which is less than 1 or greater than gamma. This is a promise problem, which means that we believe that one of the two conditions is true. The difficulty of this problem depends on the size of the gap gamma, and it is already known to you because it's been shown previously in this course that when the gap is exponentially large, then the problem is easy, and it is difficult when the gap is constant. We say difficult, we may mean unsolvable in polynomial time, depending on your belief in complexity theory conjectures. But as usually happens in cryptography, we play in this middle area here, where the gap is polynomial in n, where we can build crypto system on top of this problem. We have no form of proof of hardness, but we have no knowledge of reasonably efficient algorithm. In this specific case, the best known is exponential in time. Before getting to the point of LWE, I won't discuss the SIS problem, which will show being sort of an ancestor of LWE. In this problem, we work with equation over ZQ, where Q, make it simple, is a prime number, and whose size is roughly the square of another parameter, which we call n here. We take n vectors AI in ZQ to the n, which we put as the column of matrix A. And we will see in a while that this matrix A is basically behaves like a hash function. And we take a parameter beta, which is the measure for what we mean saying short. So the problem here is to find a zero combination of the columns of A, which is non-trivial, and also where the coefficient Zi are integers and such that the norm, the L2 norm of this vector Z is sufficiently small. So we are looking for a solution of this problem, A Z equals 0, where Z is a vector of integers with a small norm. Yeah. Just a moment, sorry. Yeah. It should be noticed that this problem is easy, of course, when we have no constraint on the size of Z, and that is because we can run Gaussian elimination and solve that easily. It should also be noticed that this is a lattice problem. In particular, it is an SVP problem in this setting L, in this lattice L perp, which is defined in this way. But you could be wondering on why does SIS even admit a solution? And actually, this is true only if the parameters are chosen carefully. I want to convince you in a while of this thing. So we want to consider this function which goes from 0, 1 to the m to zq to the n, which takes a vector, a binary vector of length m, and associate a times x. So let's consider the case when the domain is larger than the codomain. So we have that the size of the first set is larger than the size of the second set. So we have that 2 to the m is larger than q to the n, and so m is larger than m log q. In this setting, this function is not injective by a counting argument. And so there exists x different from y such that ax minus y is equal to 0. And this guy here, we can call it z, and z is different from 0. And what we have about z is it's that its L2 norm is not larger than the square root of m, because its entries can be just 0 or 1. So if we set beta to be larger than the square root of m, and if we set this constraint, those two conditions together say that there exists z, which is a solution to the problem SIS. So yes, we can see that solution exists, and basically we have shown that if this problem is hard, then this function behaves like a collision resistant hash function, for the simple reason that once we manage to find a collision for this hash function, then we manage to find a solution to the SIS problem, which is assumed to be hard. But what we mean by hard, to understand this, we need to refer to this famous theorem, which says that solving SIS is at least as hard as solving GapSVP. This theorem tells us more, because what the theorem says is solving SIS with non-negligible probability is at least as hard as solving GapSVP on every lattice with probability close to 1. This, from a cryptographic point of view, is a powerful result, because it means that whenever we manage to break the average case SIS, and when we mean average case, we are saying crypto, because keys are generated randomly, for example, then we manage to break every instance of GapSVP problem, which is believed to be hard. So this result proves a worst case to average case reduction for this problem. Okay, let us now consider an apparently different problem, which is solving a set of linear equation over Z. So this is easily solved when sufficiently many equations are given by Gaussian elimination, right? But what if the equations are not tight? So for example, what if I'm okay in this first equation if I get 8, but also I'm okay if I get 7, and I'm okay if I get 9, and for example, I'm not okay if I get 10. So if I need to consider the equation valid up to a small error, which in this case may be minus plus 1. So what if I want to solve this system of equations? Well, in this case, Gaussian elimination simply does not work, because all the operation that we need to perform to do Gaussian elimination, we will basically only amplify the size of the error, making the new equation, so the obtained equation, uninformative. So this problem is learning with errors, is finding the solution of systems of equation like this one in presence of errors. So to be more formal, we have M integers modulo Q, which are the guys here, that are computed as the scalar product of given vector AI in ZQ to the n with a secret fixed vector S, plus a random error epsilon 1, epsilon 2, epsilon n, and all those guys are drawn from error distribution, which is called chi. If we want to write this in a more compact way, we are looking for a solution to AS roughly equal to B. This roughly depends on the distribution. Again, is finding S solvable? We should ask this question. And actually, it depends again on the choice of the parameters, but in this case is a little more subtle. I just give you now a couple of examples to make you in order to make it clear why this can be solvable in some cases. Let's go before to the extremal cases when chi is the uniform distribution of ZQ. Then in this equation here, I cannot read any information on the guy S, because the information on S is completely masked by the error. So in this case, there is no way to find the solution. Let's go to another extremal case, which is for making it simple, n equal 1, and the distribution of errors is minus 1, 0, 1. Then, in this case, if B is being sampled like a LWE sample, then in one of these three equations, we have a zero factor. So if I consider this cubic equation in S, this has to be 0 because all the possible errors have been listed. The idea, I'm just oversimplifying here, so just take the idea of this. The idea is that if I take sufficiently many samples of this, I have sufficiently many cubic equations that I can then linearize, and I can solve the problem. In this way, it is possible to prove that the solution exists, but also it is possible to prove that it is hard to find, since the complexity of this algorithm is exponential. Now I need to give you some information on the random distribution, because it is common to start from a normal distribution with zero mean, which means small errors, provided, of course, some necessary roundings, because we are working here on modular integer, and whose standard deviation is a small fraction of Q. This is done basically to make more likely only small errors, like you can see in the drawing. Of course, this is circular, so I need to make it like that. But only errors which are close to 0 are more likely than others. Okay, LWE comes in two versions: search version and decision version. Search version asks you to provide the correct S with high probability. Once you are given some noisy products calculated before with a fixed secret S. The decision version of LWE is instead, you are given A and B, a matrix and a vector, and you need to distinguish if B is being sampled starting from A and from a secret vector, or if it is just been taken randomly. So if AB represents a correct LWE sample, or if it is just a random pair of matrix and vector. It is not hard to prove that if we know how to solve search, then we know how to solve decision. I will show this, but it's very easy. So if S is an oracle which can solve search with high probability, and assume that this is a challenger which is challenging us. So let's play the following game. They can send us many triples AI, BI, and TI. Some of them have been generated according to the LWE distribution with a fixed secret S, and other are taken randomly. This is known, so we know this. At some point, the challenger provides us with a pair A0, B0, but we don't know if it is LWE or uniform distribution, and we need to tell if it is the first or the second. Well, this is easily done because we can go to the oracle which solves LWE. We can give to the oracle all the pairs which belong to the LWE distribution, and we get back the secret S with high probability. Now that we have the secret S, we can get back to our challenge, and if the scalar product of A0 and S minus B0 is a small number, it's close to 0, then we can bet that the pair comes from LWE. Otherwise, we can bet that it doesn't, and so it is random. And we will win this game with high probability. So this is the easy decision to search reduction. But these problems allows also for a search to decision reduction. In particular, there's this theorem due to Regev that can prove that if we have access to a procedure that is able to distinguish for all S LWE sample from uniform samples, then we can access to a procedure which, given some samples generated with an unknown S, provides the correct S with a probability. This is more tricky. I just wanted to give you the hint for the proof, but I'm gonna hide the most important part for the sake of time. So we are playing with S this time, and we first receive many pairs AI, BI, which comes from the same LWE sample with the same secret S. And the challenge is to find S. The idea is that we can guess each component of S. For example, we can start asking ourselves, I don't know, if S is S1 equal to 7, what we can do, and this is the part that I'm hiding, is incorporate this assumption in the pairs, and I give the modified version of these pairs to the oracle, which can distinguish LWE from random. If the oracle on these modified pairs can still see LWE, then it means that our guess is correct. This is to be proven, but it's true. Otherwise, the guess is not correct. So if my first guess on S1 is correct, I'm okay, I go to S2. Otherwise, I can change my guess on S1. And this is done polynomial number of times. And so this proves that if that search LWE reduces to decision LWE. LWE is a lattice problem, at least in its search version, and you can convince yourself that it is an average case bounded distance decoding problem on this lattice here, where the goal is to find the vector of the lattice, which is the closest to B. And in particular, when parameters are set correctly, with very close, we mean that very likely you're going to have only one solution to the problem. There's this famous link with SIS, which can be proven as an exercise, which tells you why we call one problem the dual of the other. Because if you look at the lattice of LWE, you see that it is basically the dual of the lattice of SIS scaled by a factor Q. Let's talk now about the hardness of LWE. Famous theorem, hard theorem from Regev, actually from 2005 in the first version, proved that if there exists an efficient algorithm which solves LWE, then you can instruct a quantum machine to solve GapSVP. This is not exactly what we wanted, because it means that so we believe that this GapSVP is hard on classical machines. We also believe that it is hard on quantum machines, but of course our knowledge on quantum machine and quantum algorithm is less deep than it is on classical. And so we would prefer actually to have this result classical. Actually, in 2009, this has been made classical, but with an exponential modulus, which is far from being usable in cryptography. But then the reduction recently has been made classical with any modulus. However, apparently, this setting here of the first theorem is the most the better for applications. So just to recap, we know that GapSVP quantumly reduces to search LWE, which reduces to decision LWE. And on top of decision LWE, we want to build all our LWE-based crypto systems. What we obtain from this is that if one managed to break an LWE-based crypto system, then that algorithm can be used to solve decision, which can be used to solve search, which can be used to produce a quantum algorithm which solves GapSVP. And we believe it is not doable. So the security of LWE-based crypto system in this sense are based on this GapSVP problem on lattices, on general lattices. There are many applications to cryptography or of LWE. Some of them will be discussed in the next lectures. You can see here a list of standard and non-standard cryptography, which can be done using LWE. I'm not gonna enter into the details of this because I want to tell you more about structured LWE. So when you go for application of LWE, there's something you immediately realize. It is that the size of the information is too large. You need to store, for example, this large n times n matrix. You have a quadratic size to store, and this is not good for application. So the idea is that you can replace actually this matrix with the matrix with less entries, with a bit of redundancy. So for example, you can consider some structured matrix with a circular idea like this. So you need to fix only one column, in this case, A1, A2, A3, A4, and then you reproduce all the other columns just as a permutation of this one. In terms of memory, you are storing a column for building a matrix. Why exactly this permutation? Because you may notice that multiplying this matrix for a vector S, S1, S2, S3, S4, for example, is equivalent to solve this equation here. So I call this A, I call this S, I call this B, this equation A, S equal B, where A, B, and S are polynomial in this structure here, which is set Q of X over X to the 4 minus 1. Actually, this is not exactly good for cryptography, so we need to swap to another structure. We just need to replace minus with plus, which means that we need to put a minus on close to this element, and then multiplying by that matrix is equivalent to solve for a polynomial in this ring. And this is why this is how we obtain what we call ring LWE, which is something you can learn on this famous paper, for example. If we want more structure, we use what we call module LWE. You will see application of this tomorrow. And the idea of module LWE is to replace that random matrix with a block matrix, and each block is a structured matrix like in the previous slide. So each block of this is exactly one of those. And so basically this part of the matrix is a multiplication with a given polynomial, and A11, this is on the multiplication with polynomial H1 and so on. Most popular case is rank 3 module LWE, where we have this 3 times 3 matrix where each entry is a polynomial. And so we can expand it like a circulant matrix as before. Complexity-wise, we have similar results to those shown for LWE. So we have a reduction from mod GapSVP. This result is recent. You can read it here. You can read it here. So what it means is that if we manage to solve rank 3 mod LWE, then we manage to break the GapSVP problem. The only difference is that we are not looking now on general lattices, because that is not a general lattice, but it is a lattice which is coming from a matrix with a precise structure. And so then we call mod GapSVP the shortest vector problem with gap on that specific kind of lattices. This is the end of the presentation. I leave you here some of the references that can be studied to learn something about LWE. And I thank you for listening.